Okay, so this is Zoom Lecture 12, which happens to be exam review number 2. And hopefully, after you have reviewed exam review number 1 and you've completed exam review number 2, you will feel much better prepared for the final exam. Please keep in mind that I've also posted reviews of all of the quizzes that you've taken as well. And again, the problems on the reviews may be slightly different, but the procedures are exactly the same. So I would encourage you to go through the exam reviews and all of the pre-recorded quizzes, those that I've gone over, and I think if you understand those things, you'll do very well on the final exam. So let's start with problem number 1 here. If the cost of producing X items of a product is given by the cost function, C of X is equal to 10X plus 100 on the square root of X plus 10,000. Determine the marginal cost when X is equal to 100. Now you should recall that the marginal cost is found by taking the derivative of the cost function. And we know that the cost function is 10X, let's see, plus 100 on the square root of X, but I'm going to rewrite that as 100 times X to the power of 1/2, because X to the power of 1/2 is the same thing as the square root of X, but writing it this way will allow me to use the power rule more directly. Plus 10,000 and again, we need to take the derivative of the cost function, and that would give us the marginal cost. I guess I should say the marginal cost function. And the derivative of 10X is 10. And luckily, the derivative of 10,000 on the end there just zeroes out. And the derivative of 100 times X to the power of 1/2 is going to be 1/2 of X to the power of negative 1/2. And we could simplify this as 10 plus 1/2 on the square root of X. Okay, so that's going to be the function for the marginal cost. And the question is, determine the marginal cost when X is 100. Well, let's go to the simplified version. That's going to give me 10 plus 1 divided by 2 times the square root of 100, right? Because X is 100. And the square root of 100 is 10, and 2 times 10 is 20. So it appears to me that we have 10 plus 1/20, and 1/20 is 0.05, so that's going to be 10.05, which tells me the marginal cost when X is 100 is going to be $10.05, right? This is money we're talking about, so $10.05. If they had been asking for the marginal revenue at a particular value of X, then we would take the derivative of the revenue function. If they had been asking about the marginal profit, we would first have to write the profit function, which is going to be revenue minus cost, and then we would just take the derivative of that. So that takes care of problem number 1. Problem number 2. Now, problem number 2 is asking us to use implicit differentiation. And remember, we can use implicit differentiation to find the derivative of those things that are not functions directly. For example, if you have an ellipse is not a function, but if you happen to know the X and Y value for a particular point, you can still find its derivative. You can still find the slope of the tangent line at that point. The reason you have to have x and y is because this not being a direct function, it would actually have at least perhaps more than one value, more than one point at the same x value. So you have to have x and y. But let's go ahead and do this. Remember that y is a function, and we have to employ the chain rule. And the derivative of 3x squared is 6x. And to take the derivative of 4y squared, again, y is a function. And it's going to be 8y, which is just power rule. But since it's a function raised to a power, it's going to be 8y, y prime. The derivative of -2 is 0, and the derivative of the 7 is 0. And if I want to get y prime by itself, I will subtract 6x from both sides. That will leave me -6x on the right side. And then to get y prime by itself, the next step would be to divide by 8y. And 6 and 8 are both divisible by 2, so I could actually reduce this down to -3x over 4y. Now you tell me what x and y are, and I'll plug those in, and I can tell you the derivative at that particular point. Let's look at number 3. Again, use implicit differentiation to express the derivative of y with respect to x. And here we go. The derivative of 9x is 9. And then to find the derivative of the second term, let's see, I'm going to let 2x be one function, and I'll let y be the second function, and I'm going to have to use the product rule. So let's see. I guess I'll put a bracket here to help keep up with what's going on. So I'm going to multiply my first function, which is 2x, times the second function, and the derivative of y is y prime. So that's the first function times the derivative of the second. Then I have to add to that the second function, which is y, times the derivative of the first function, and the derivative of 2x is 2. And I'll just slide that in right here in the front. And it appears that my computer is taking a break, and by now we should be used to that, right? Okay, looks like we are finally back in business, and it looks like some stray marks have appeared. Let me see if I can fix these things quickly so we can get back on track. Let's see, I multiplied 2x times the derivative of y, added to that y times the derivative of 2x, which is just 2, and then the derivative of 2 on the right side, since 2 is a constant, it'd be a horizontal line, right? So its derivative would be 0. So once we take the derivative, this is what we have. And I'm going to leave this -2xy on the left. I'm sorry, -2xy prime on the left. And that's going to force me to take the -2y to the right side, and also take the +9 to the right side. So that's going to end up giving me 2y minus 9 And all I have to do now to get y prime by itself is just divide both sides by negative 2x. So again, you tell me what x and y are, and I'll plug those in, and I can give you the derivative at that particular point. So again, this is implicit differentiation. Students tend not to struggle too terribly with implicit differentiation, but if you're still having trouble, go back and go through the textbook, go through the lecture notes, and again, go through the quizzes, and hopefully that will serve as a good reminder on how to do implicit differentiation. Let's look at problem number 4. On problem number 4, we're told to suppose that the velocity of an object is determined by v of t is equal to 3t squared minus 5. Find the distance traveled from 0 to 4 seconds. Okay, so we know that if you integrate the velocity, it will actually take you to the position function. And if I integrate this, that's going to give me 3t cubed over 3, which is just t cubed. And then I'm going to subtract from that, and I have to integrate the negative 5 or integrate the 5. That's going to give me 5t. Okay, so if I take the integral, again, of the velocity, if I take the integral of that with respect to t, then that would give me the position equation. Okay. And I have to integrate that as t goes from 0 to 4, right? So once I take the integral, that's going to give me t cubed minus 5t. And I'm evaluating this from 0 to 4 seconds. That's a 4, terrible 4. Let me try again. Okay. So what do we do now? Well, we plug the 4 in and evaluate, then we subtract, and then we plug the 0 in and evaluate. Well, 4 cubed, 4 times 4 is 16, times 4 is 64, so that ends up being 64 minus, and then 5 times 4 is 20. And luckily, that lower limit, or the lower bound, is actually a 0. And when I plug 0 in for t, in both of those terms, I just get 0. And 64 minus 20 is 44. So that means we have a distance of 44 units. 44. So again, if you know the position equation, you take the derivative and you have the velocity. But the opposite of that is knowing the velocity, taking the integral, and that gives you the position equation. And then you can evaluate the integral and you have the total distance traveled. Number 5, consider the graph y is equal to x cubed plus 1. Find the area under the curve that's above the x-axis as x goes from 0 to 2. What would the area be from -1 to 0? And then finally, what would be the cumulative areas? And what would be the integral as x goes from -2 to -1? So this has a lot of subparts to it. So let's go ahead and answer the first question. The first question says, or the first direction is to find the area under the curve as x goes from 0 to x is 2. Well, x is 2 is here. And that's going to be, if I can draw a straight line down, a vertical line. This is just a rough sketch. As x goes from 0 to 2, I'm basically looking for the area all inside here, right? All of this area here, as if we were painting above the x-axis, but trying to stay below the curve. What would all of that area be? And I could continue to fill this in. I could take hours, I guess, or several minutes to get this done. Not going to do that, but I think you get the idea. What is the area of this shape here? And again, that's going to be the area bounded by the x-axis and the function. And to do that, I'm just going to take the integral as x goes from 0 to 2. And I have to take the upper function minus the lower function, right? Remember that? I could sort of imagine a rectangle being here. And the upper function is just x cubed plus 1. The lower function is y is 0. So there's really nothing to write for the lower function. So I'm just going to evaluate x cubed plus 1 with respect to x. And if I integrate x cubed plus 1, I get x to the power of 4 divided by 4. And the integral of 1 dx is x. And again, we're going from x is 0 to x is 2. And now we'll plug in the upper bound and subtract the lower bound. Well, capital F of 2 is going to be 16/4, which is 4, plus 2 is 6. And I'm going to subtract the lower bound. And luckily, again, our lower bound is 0. And if I plug 0 back in for both terms, I end up getting 0. So that tells me that the area is 6 square units. 6 square units. Okay, so that takes care of that part. And then it says, what would the area be from -1 to 0? Well, that's not going to be too bad, because between -1 and 0, we're just trying to figure out the area of this little purple shaded part here, right? It's above the x-axis, but below the curve. What would that area be? Same process. We're going to evaluate from -1 to 0. It's the same function, right? It's still the top function, which is x cubed plus 1. With respect to x. And if we integrate, we still get the x to the power of 4 over 4 plus x. But all we have to do now is plug in -1 and 0. Okay, if I plug 0 in to this function here to evaluate, I get 0 over 4 plus 0, that's going to be 0, minus, and now I have to plug in that lower bound, which is -1. Well, -1 to the power of 4 is 1, and 1 divided by 4 is 1/4. And then I'm going to plug -1 into the second term, that's going to be -1. And if I go inside the brackets, 1/4 minus 1 is -3/4, but I have a minus out front, so that area is actually going to be +3/4. Remember, area is always positive, so the area here, +3/4. And then it says, what would the cumulative area be? In other words, if I add those two together, well, that's just going to be 6 plus 3/4. So 6 3/4 or 6.75 would be the total area. That would be the area of the red region, which we found first, plus the area of the purple region. That's what we figured out secondly. Okay, so let's move on to other parts here. What would be the integral if we go from -2 to -1? Well, -2 to -1 is here. It would be here. What would the integral be? Well, if I integrate from -2 to -1, and again, let's see. I'm going to integrate, and the function is x cubed plus 1. With respect to x. Now we know this time that the graph is below the x-axis. So what does that mean? Keep that in mind as I continue to work this. So I've got x to the power of 4 over 4 plus x. And we're going to evaluate from -2 to -1. So that's going to be 1/4 minus 1. I got that by plugging -1 into both terms. And then I have to subtract and plug in -2. Well, -2 to the power of 4 is 16, and 16 fourths is 4, and then 4 minus 2 is 2. I'm going to make sure I did that correctly. Give me just a second to check this. Yes, so we're good. Now remember, 1/4 minus 1 is -3/4. And then I have to subtract 2. And 2 is 8/4. So it looks to me like -11/4. Okay. You may be wondering, why do we have a negative answer? Well, because when you evaluate the integral, you end up getting a negative answer if the graph is below the x-axis. But what if you wanted to know the area? In other words, what if you wanted to paint this? How much area would that be? Well, remember, area is always positive, so we just take the absolute value. So the area would be positive 11/4, but the integral is actually -11/4. So make sure you understand the difference between being asked for the area and being asked just to evaluate the integral. Okay. There's another way to solve this, but I think I'm not going to show you because I don't want to create confusion. So if you noticed my hesitancy there, I was just trying to think about whether or not I should show you the other way. Not going to do it today. And let's look at problem number 6. Here we have a piecewise function. And the first function is graphed in blue. That's f of x, which is equal to x squared. And we're on that function if x is less than 0. And then if x is greater than or equal to 0, then we're on the line y is equal to x, which is graphed in red. And the question is, what would be the area under the curve between x is -1 to x is 3? Well, x is -1 would be about here, and x is 3 would be about here. And we just want to know, what would the area be? Well, luckily, both of these functions are above the x-axis, so we don't have to worry too much about the negative situation. So if we wanted to shade all of this here, all of this, and also shade the area of this triangle, I could actually use geometry, couldn't I, to get the area of that triangle there. But anyway, if we were going to shade all of this as well, the question is, what would be the area under the curve as you go from -1 to +3? Well, this is going to be two different integrals, right? Because we have two different functions. We literally change functions when we get to 0. So this is what the setup would look like. First, we would integrate with f of x. We would integrate from -1 to 0, because if you're under the blue function, right, x goes from -1 to 0. Remember, we always read graphs left to right. So the integral from -1 to 0 for x squared with respect to x, that will give us the first piece of area. But then we would have to add to that the integral as we go from 0 to 3. And that would be for the other function, which is x. And again, this is with respect to x. So that's the setup. I apologize for the handwriting, but that's what it is. And let's take the integral. Well, if I integrate x cubed, that's going to give me, if I integrate x squared, that's going to give me x cubed over 3. I was doing a little anticipation there. So x to the power of 3 over 3. And I'll have to evaluate that as x goes from -1 to 0. And then I have to add to that the integral of x dx, which is x squared over 2. And we will evaluate that one as x goes from 0 to 3. And now we just plug in the upper bounds minus the lower bounds for each of these. When I plug 0 in, I get 0 cubed over 3, which is 0. And then I have to subtract, and then I'll plug -1 in. So that's minus a -1/3, which makes that positive 1/3. And let's do the second part. Let's plug in 3 for the upper bounds. 3 squared is 9. 9 divided by 2 is 9/2, or 4.5. So I've got 9/2. And of course, when I plug the 0 in, luckily in this case, everything zeroes out. I guess I better get a common denominator. So I'm going to let 6 be the common denominator. And 3 goes into 6 2 times. So that's going to be 2/6, which is the same thing as 1/3. And then let's see, if I divide 2 into 6, that's 3 times, and 3 times 9 is 27. And 2 plus 27 gives me 29, so 29/6. Okay, so that's going to be about 4 2/3. No, I apologize. 6 goes into 29 4 times with 5 left over, so 4 5/6. Square units. Remember, area is always in square units. So I figured out that the area of this piece here under the curve is actually 1/3. And then we figured out that the area of this triangle here is 9/2. And then once we got a common denominator, we ended up getting 2/6 plus 27/6, which is 29/6. And 6 goes into 29 4 times. That's 24 with 5 left over out of 6. So 4 5/6 will be the total area underneath that piecewise defined function. And finally, problem number 7. Problem number 7, they tell us to evaluate the integral using substitution. I decided to give you a little bit of a hint there. Remember, we use substitution if we have to do the opposite of the chain rule to make it work. And I'm going to let u equal x to the power of 4. Because I'm hoping that's an e to the u du situation, right? So if u is equal to x to the power of 4, then that means du over dx would be 4x cubed. So du itself would be 4x cubed dx. Okay. And again, I'm trying to make this an e to the power of u du. Well, we're going to have to do some fancy footwork here because I need 4x cubed dx, not 3, to make that an e to the u du. So I'm going to take that 3 to the outside, not a big deal, and I'm going to now evaluate e to the u. And remember, du would have to be 4x cubed, which means I would have to put a 4 there, but then I would have to divide by 4. Remember that? Because du would be 4x cubed dx, and I only had x cubed dx, so I'd have to put the 4 in there to create my du, but then divide by 4 to balance it back out. And then we're basically done at this point because the integral of e to the u du is just e to the u. And I'm going to make the final answer in terms of x. So that's going to be x to the power of 4. And I will say plus c because this is an indefinite integral. And that is the conclusion of your cumulative exam review. Now, I know that was a brief review, but it did cover a lot of topics. So again, I advise you to go back and watch exam review 1. You might want to rewatch exam review 2. And if you go back and watch the quizzes, the quiz reviews that I've posted, I think you should be in great hands as far as going into the final exam. Thank you.